Hello everyone, I am Chen Guangzhu, the teaching assistant for this course. Today I will host the second problem session. We will discuss several topics which cause confusion in some students, and this will include cleaning star and paths in the DFA. Then we will show the solution for the first challenge problem. Let's begin with cleaning star. Cleaning star is an operation on regular expressions. For example, we can have 1 star, where 1 is a regular expression of length 1. However, there is a common misconception that 1 star is an infinite long string of 1s. This is not the case. In fact, 1 star is still a regular expression, whose language, L1 star, is the set of strings of 0 or more 1s. Although this set is infinite, each element in it has finite length. This is similar to the set of integers, where the set is infinite, but each element it contains is finite. Now we come into the topic of infiniteness. As we know, infinite objects are important in mathematics, like the set of integers or a line that contains an infinite number of points. Yet, in a computational model, a computer can never get an infinite input, unless you can represent it in finite form. For example, we can represent a regular language with a regular expression which has finite length. We can also store 3 numbers as parameters for a line. In such cases, we extract important information that can represent the whole set. This concept is a bit like sufficient statistics, in case you have heard of it. Now we will take a minute to discuss a fallacy we found in the forum. In the thread, it talks about a DFA that accepts all strings of 0s and 1s except those whose last character is 1. Then a student asks, what about the string 1? Basically, sometimes we fall into the fallacy that you cannot have a last character unless you have other characters. This is not true. In fact, if we resort to strict mathematics, we would define that for n greater than or equal to 1, the last character of any string a1, a2 through an is just an, period. Thus, coming back to the question, the string 1 is not accepted by this DFA, because the last character is 1. Another thing worth mentioning is that the empty string, epsilon, has no last character. Thus, the statement its last character is 1 is false, so epsilon is accepted by the DFA. We will now start to discuss the conversion from a DFA into a regular expression. Firstly, let's have a review. In the conversion, we introduce the notion of k-path induction, where Rijk is the regular expression for the set of labels of k-paths from state I to state j. This means that, starting from I, if the DFA receives any string from Rijk, it will go to state j and will not pass any node with label greater than k. And Rijk describes all such strings. In the lecture, we gave a way of computing Rijk, which is either via not going through state k or going through k 1 or more times. This gives us a formula. Rijk is Rij k minus 1 or Rik k minus 1, Rkk k minus 1 star, and Rkj k minus 1. Now let's take a closer look. In the illustration, we can see that Rik k minus 1 corresponds to the part from I to the first encounter of k. Then all parts between k can be described by rkk, k minus 1. As we do not know how many times the path will go through k, we use rkk, k minus 1 star. In the end, we have rkj, k minus 1, which corresponds to the label of path from the last encounter of k to j. Here, we point out that the labels of the path from the first encounter of k to the last can also be represented by rkkk. Because it is just a path from k to k, going through nodes with labels not greater than k. And in edge cases, both rkk, k minus 1 star, and rkkk contain epsilon, the empty string. In spite of the equivalence, we pick rkk, k minus 1 star because this will give us a formula where quantities with a higher superscript will always only depend on quantities with lower superscript, which makes the implementation and understanding much easier. Lastly, we will show our solution to the first challenge problem. The problem says that L is a language with alphabet 0, 1, and 2. L contains no strings that have 3 consecutive zeros, 3 consecutive 1s, or 3 consecutive 2s. For example, the string 11000220 is not in L because it contains 3 consecutive zeros. The task is to prove that L is regular and then give a DFA for L. Firstly, we can prove that the complement of L has a regular expression, which is in this form. We have 3 consecutive zeros, or 1s, or 2s, with any number of zeros, 1s, and 2s before and after. This regular expression exactly defines all strings that do contain 3 consecutive zeros, or 1s, or 2s. Additionally, we have the nice property that regular languages are closed under complement. So it follows that L, the complement of the language of this regular expression, is regular. To construct a DFA for L, it turns out that we can directly do it without the trick of union or complement. We define the state to represent the run of the same symbol that appears at the end of the string. Specifically, we will have start state S, which we enter only initially, when the input string so far is epsilon. Then we have state A0, A00, A1, A11, A2, and A22, and a dead state D. The intent is that if the current string read in contains any 3 consecutive zeros or 1s or 2s, the DFA will fall into D and stay there. Otherwise, say the string has ending 012011, the DFA should go to state A11 because it denotes that the string has 2 1s at the end. Here is the final transition table for the DFA of L. Note that whenever we already have 2 zeros, which is described by A00, an additional 0 will kick the DFA into the dead state D. But character 1 or 2 will shift the state to A1 or A2, as now the longest run of symbols at the end is a single 1 or a single 2.